Okay, in section 17.8, we're going to be talking about Moore's circle for uniaxial stress. Okay, so a graphic method of solving stress at any point was developed by Otto Moore in 1882. He constructs a circle that shows all the combinations of normal and shear stresses at that point. It can be used as a completely graphical solution method. If you were to draw everything to perfect scale, or you can use the circle as a geometrical construction, if you will, and then use trigonometric computations in addition to the graphical construction. That's pretty much how it's mostly used. I don't see people generating these Moore circles to scale these days. I don't think you're going to be doing it. We're going to have an example on that. So the rest of 17.8 was essentially a sample. So we're going to work this example in your example problems, so please take a look at it. But let's talk about it generically here. In this section, we're going to look at example 17.9. It's Moore's circle for uniaxial stress. There's only stress in the y direction. There's no stress in the x direction in this element. Okay, so sigma y equals p over a. That is our stress. Sigma x equals 0. And then in this particular case, at this element and this orientation at 0 degrees, our shear stresses are 0. So a generic Moore's circle kind of looks like this. Okay, so what we have here is we have the shear stresses are plotted on the y-axis, the ordinate. The normal stresses, that's due to bending or tension, whatever, that's plotted on the x-axis, the abscissas. Okay, so we have shear stress plotted against normal stress. In this particular case, our maximum normal stress in the y direction is the sigma y, that is p over a, and what we're talking about is p over 2a over p over 2a. We have no stress in the x direction, so therefore this is 0. So this Moore's circle is going to be tangent to the y-axis because our stress, our normal stresses in the x direction are 0. Okay, and then therefore our radius of our Moore's circle is p over 2a, p over 2a. Okay, so when we look at this circle, we're capturing our maximum normal stress in the y direction here at sigma y. And if we notice, our shear stresses, our absolute maximum, are at these 2 points right here. Okay, those are our maximum shear stresses. Maximum shear stress here, and then, it has to be negative in the other direction. So that one's over here. So again, if there's any compressive normal stresses, they're going to be on this side of the y-axis. So this is our generic Moore's circle. And really what happens here is that if we look at this 2 theta, this sigma n, and then tau s, these are the things that we can find. These 3 highlighted variables are essentially, I think I wrote it up in the next slide. Okay, Moore's circle relates the shear stress tau right here, the normal stress sigma right here, and the orientation to theta as points on a circle. Okay, so principal stresses and max shear stresses can be easily found. Okay, and then principal planes and max shear planes are easily found by this 2 theta location. Okay, so that's how Moore's circle works, and we're going to, like I said, there's more examples in your problems folder, so we're going to check those out. Again, Moore's circle can be drawn to scale, and the magnitude of the normal shear stresses can be measured with a scale. But more typically, once the circle is constructed, the values are calculated using trigonometry. Because, we're by using the circle, we can look at triangles. We can look at these angles. We can figure this out using our basic trigonometric functions. Okay, so then here is another Mohr circle example. This is the one that we're going to be looking at for example 17.9. Okay. Now, in section 17.9, we're going to get a general state of stress. So 17.8, we were talking about a specific example of a part that did not have any stresses in the x direction. Okay, the Mohr circle is generic. There's a general state of stress, and then we can consider the this basic procedure, if you will, for drawing a Mohr circle. And then I have a handout of this procedure as it's written here in the materials folder. Okay, there's 10 basic steps. The first one is sketch the stressed element showing all of the applied stresses. That usually comes to you as the problem statement. Set up the rectangular coordinate system for the circle. Okay, that is, the x-axis is the normal stresses, the y-axis are the shear stresses. 3, follow the appropriate sign conventions. So tension's positive, compression's negative, and then shear will be clockwise rotation is positive and counterclockwise rotation is negative. Step 4, plot the normal stresses sigma x and sigma y on the normal stress axis. Plot the shear stresses, plus or minus tau, associated with the normal stress for the vertical face and the horizontal face. Label those points x and y, and we're going to go through this in an example in your example problems. Draw the XY line on Mohr circles. 7, determine the principal stresses and the maximum shear stresses. 8, determine the angle 2 theta P1 and or 2 theta P2 measured from the X end of the reference line. Determine the 2 theta PS. Okay, so this is how far you have to rotate your point to get to the principal plane 1. This is how far you got to rotate the point to get to principal plane 2. And then this is how far you got to rotate that orientation to get to the maximum shear stress. And then you're going to sketch the 2 rotated shear elements, one to show the principal stresses and one to show the maximum shear. We're going to go through another problem just like this. Okay, so for at this point, what I want you to do is review the movies for the examples for Mohr circle. There's 3 examples in there. One for the equations from 17.7, one from the example of 17.8, and then another example from 17.9. And that will help clear this up. Thank you.